Welcome back to AI.Code.Cast, everyone. Ready for another deep dive?
Always.
Awesome. Today we're tackling a classic coding problem, something you might have come across in an interview, or just as a good algorithmic workout. Merging sorted arrays efficiently.
Yeah, it's one of those deceptively simple problems. You look at it and think, oh, that's easy, but then,
Exactly. There's a lot more to it than meets the eye. We've got 3 different approaches to explore today, each with its own pros and cons. But before we jump into solutions, let's lay out the problem itself.
sounds good.
So imagine you have 2 sorted arrays, nums1 and nums2. The goal is to merge them into a single sorted array, but here's the twist. You have to store the result right back in nums1.
The key here is that nums1 has extra space at the end to fit all the elements from both arrays. That's a pretty important detail that'll shape how we solve it.
Right, it's like having a container that's just the right size to hold everything. Let's say, for example, nums1 is 1, 2, 3, 0, 0, 0, and nums2 is 2, 5, 6. Those zeros in nums1, that's our extra space. And after the merge, nums1 should be 1, 2, 2, 3, 5, 6.
Yeah, and this problem isn't just a theoretical exercise either. It pops up all the time in real-world stuff like database merging, combining sorted lists, all sorts of practical applications.
Absolutely. So let's start with the most basic approach, the brute force method. Without thinking too hard about efficiency, what would be your first instinct to solve this?
The most straightforward way would be to just copy all the elements from nums2 into that extra space in nums1, and then you just sort the whole combined array. Simple as that.
Yeah, it's like taking 2 stacks of sorted cards, putting them together, and then sorting the whole deck again. But what about the efficiency? Any downsides you see with this approach?
Well, the copying part is pretty quick, but that sorting step can become a real bottleneck, especially if the arrays are huge. The time complexity will depend on the specific sorting algorithm you use, something like merge sort or quick sort.
Right, and sorting large arrays can take a lot of computational power. So while this brute force method is super easy to understand and code up, it might not be the best when performance really matters.
Exactly, and that's what makes this problem so interesting, because the limitations of the brute force approach kind of push us to find more clever, efficient solutions.
Right, so let's brainstorm for a minute. How can we avoid that expensive sorting step?
Okay, well, we know both of the input arrays are already sorted. Maybe we can use that to our advantage.
Yeah, maybe we can merge them directly without having to resort the whole thing.
Yeah.
What if we use multiple pointers to kind of keep track of where we are in each array as we're merging?
I like that. Like one pointer for each array and then maybe another one for our final merged array, which is really just nums1 since we're merging everything right into it.
I'm with you. So we start with all the pointers at the beginning of their respective arrays, compare the elements they're pointing to, and put the smaller one into nums1.
That's the idea. And then you move the pointer for the array you took the smaller element from so it's ready for the next comparison.
Hold on a sec. If we keep moving forward like that, won't we end up overwriting some of the elements in nums1 before we've even had a chance to compare them?
You're right. That's a potential snag. We definitely don't want to accidentally erase any data.
What if we flip the script? Instead of starting at the beginning, we start at the end of the arrays.
Now you're talking. Starting from the end and working our way backwards, we could avoid overwriting anything in nums1. So, are we thinking a 3-pointer approach then?
Let's explore that.
Okay, so we're going with this 3-pointer approach, starting from the end.
Yeah, like we were saying, to avoid overwriting any of those precious numbers in nums1.
Right. So picture those 3 pointers.
One for nums1, one for nums2, and one for the final merged array, which is really just nums1 again, since we're doing this all in place.
Exactly. We'll set these pointers to point to the last meaningful elements in each array. So for nums1, the pointer would be at index m1, where m is the number of elements. For nums2, it'd be at n1, with n being its size. And for the merged array, well, it'll be at m plus n1, which is the very last position in the expanded nums1.
It's like we're carefully backing into a parking spot. Got to be precise to avoid any fender benders.
I love that analogy. So here's the play. At each step, we look at the elements our nums1 and nums2 pointers are pointing to. The bigger of the two gets placed at the spot where our merged array pointer is.
Okay, let's say nums1 is 4, 5, 6, 0, 0, 0, and nums2 is 1, 2, 3. So our pointers would start at 6, 3, and the last 0 in nums1.
You got it. We'd compare 6 and 3, put the bigger one, that's 6, at the end of nums1, and then move the nums1 pointer back one step to 5.
And then rinse and repeat. Compare, Place the larger element, move the pointer, just keep going until we hit the end of one of the arrays.
You're on a roll. We keep doing that dance until one of the arrays is totally used up. That's when its pointer hits the beginning.
Ah, but what happens when we reach the end of one array? Do we just stop there?
Not quite. Remember, the numbers left in the other array are already in order. All we got to do is copy those over to the front of nums1.
That's right. It's like half the deck is already sorted, so we just slide in the remaining cards.
Exactly. Now let's talk efficiency. This three-pointer approach, since we're looking at each element only once, the time complexity is OM plus N, which means it scales linearly with the size of the arrays.
Way better than that brute force approach. And what about space complexity? Are we using up extra memory here?
That's the cool part. We're merging right inside nums1, no need for any temporary arrays. The only extra space we use is for those 3 pointers, which is always just 3 no matter how big the arrays are.
So OM plus N for time and O1 for space constant space. This three-pointer method is looking pretty slick.
It's definitely a winner in terms of efficiency and elegance, but there's always more than one way to skin a cat, right? There's another approach we can try, using recursion, where a function calls itself to solve smaller pieces of the problem.
Recursion always gives me a bit of a headache, but I'm up for it. So
Yeah.
will we still be working with these pointers?
Not exactly in the same way, but the basic idea of comparing elements and putting the bigger one in the right place, that stays the same.
So how do we break down this merging problem into these smaller subproblems using recursion?
Think about it this way. At each step, we're trying to find the biggest number left in nums1 and nums2 and put it in the right spot in our merged array. We can do that over and over again recursively until one of the arrays is empty.
I think I'm starting to see where you're going with this. Can you walk me through a quick example?
Sure. Let's say nums1 is 7, 8, 9, 0, 0, 0, and nums2 is 4, 5, 6.
Got those visualized. So where does the recursion start?
We begin by comparing the last elements of both arrays. That's 9 from nums1 and 6 from nums2. The bigger one, 9, goes to the very end of nums1, which is where we're building our merged array.
So nums1 becomes 7, 8, 0, 0, 0. Then what?
Then we call the function again, but now we look at nums1 as 7, 8, 0, 0, 0, and nums2 stays as 4, 5, 6. See how we've kind of shrunk the problem a bit? We placed the biggest number, 9, and now we're focusing on the rest.
Right, right. So we keep comparing those last elements, putting the bigger one at the end of nums1, and doing this whole thing over and over until, what was that base case again?
The base case is when one of the arrays runs out of numbers. And when that happens, we just take whatever's left in the other array and copy it over to nums1 because it's already sorted. That's the beauty of this divide and conquer approach.
Okay, so we've got this other clever solution using recursion, but how does it measure up against the three-pointer method in terms of efficiency? I guess that's a question for the next segment, right?
Definitely something to look forward to. All right, so we've talked about 2 pretty different ways to tackle this merging problem, the three-pointer method and the recursive approach.
Right, now it's time to compare them head to head. And of course, we can't forget about our old pal, the brute force method. How does that one stack up?
Well, the brute force method, its biggest selling point is definitely simplicity, it's easy to understand, and the code is super straightforward.
But that sorting step, as we discussed, can really slow things down, especially if we're working with massive data sets.
Exactly. That OM plus N log M plus N time complexity just won't cut it when performance is key.
Then we came up with the three-pointer approach, starting from the end of the arrays. Pretty clever way to avoid overwriting any data.
For sure. And we ended up with a really nice OM plus N time complexity, which is linear.
Plus, don't forget about the space complexity. O1, constant space. We were merging everything right within nums1 using hardly any extra memory.
It really shows how a little bit of creativity can lead to a very efficient solution.
Now, about that recursive approach, I gotta admit, recursion always makes me feel like I'm going down a rabbit hole.
I get it. It can be a bit abstract at first, but the beauty of recursion is its elegance and the way it reflects that divide and conquer strategy.
We were essentially breaking down the problem into smaller, identical subproblems.
Exactly. Comparing those last elements, placing the bigger one, and then repeating until one array was empty. A very clean way to express the logic.
And the time complexity for the recursive approach also came out to be OM plus N, matching the three-pointer method.
Yeah, but the space complexity with recursion, that can be a bit trickier. Worst case scenario, we might end up using OM plus N space because of those function calls stacking up.
So there's a bit of a trade-off there. Recursion gives you elegance and readability, but you might pay for it with higher memory usage compared to the iterative three-pointer method.
Right. But there's this thing called tail call optimization that some languages and compilers support. It can actually transform certain recursive functions into iterative ones, so you don't have that extra space overhead.
So it's not always a simple choice. There are these subtle differences to keep in mind.
Absolutely. The best choice between the three-pointer and recursive approaches often depends on things like coding style, language-specific features, and the specific context of the problem.
So for our listeners who might run into this merging problem, maybe in an interview or a real project, what are the key takeaways?
If your main focus is on keeping the code simple and easy to read, and you're not dealing with gigantic data sets, the brute force approach is a decent place to start. But if efficiency is super important, that three-pointer approach really shines. Linear time and constant space complexity, that's hard to beat.
And when does recursion come into play? When would we choose that as our go-to solution?
Recursion is often a good choice when you value elegant code and that divide and conquer strategy. And like I mentioned, if you have tail call optimization, it can be just as space efficient as the three-pointer method.
It's all about picking the right tool for the job, right?
Exactly. Each tool has its strengths, and it all comes down to understanding when to use each one.
Well, I think we've given everyone a lot to think about today. We've covered everything from intuitive solutions to more sophisticated ones, from brute force to optimized algorithms.
Yeah, we've dug into how the algorithms work and also talked about the strategy behind choosing the best approach.
And that's what AI.Code.Cast is all about, giving you the tools and knowledge to tackle coding challenges with confidence and a deeper understanding of not just the how, but also the why.
Before we wrap up, I'd like to leave our listeners with something to ponder. What if you had to merge case-sorted arrays? Not just two, but any number.
Ooh, good question. That definitely builds on what we've talked about today, and it opens up a whole new set of challenges and possibilities.
Right. Efficiently merging lots of sorted arrays might lead us into the world of heaps and priority queues. But that's a deep dive for another time.
Definitely. Thanks for joining us on this algorithmic journey. Be sure to subscribe to AI Codecast for more exciting explorations into the world of code. Until next time, happy coding.